What's up guys, it's Iman Fiaz and today's video is on AQA A-level chemistry thermodynamics question paper from physics and maths tutor. Question 1, state the meaning of the term enthalpy change. Well, that's obviously just going to be heat energy change at constant pressure. Heat energy change at constant pressure. Question part B, complete the figure above by writing the formulas include state symbols of the appropriate species on each of the three blank lines. Okay, so I've got this, and that's the first ionization energy of calcium. So I've got to have so it's got to be what's it called? It's got to be atomization of calcium then, because I can see chlorine is still the same. So what it's got to be is it's got to be Ca solid plus Cl2 gaseous, and that's the enthalpy of atomization of calcium. Then this, well then this is going to be the second electron affinity, second ionization energy, sorry, Ca2 plus gaseous plus 2E minus plus Cl2. The Cl2, nothing happens to Cl2 because it's only affecting the calcium. And then the third one, well, this is just going to be Ca2 plus gaseous, electron affinity, electron affinity of chlorine, Ca2 plus gaseous plus 2 Cl minus gaseous. Use the figure in part A and the dating table 1 to calculate a value for the enthalpy of lattice dissociation of calcium chloride. So what is that? Enthalpy of lattice dissociation of calcium chloride. Lattice dissociation. So what I would do first is fill in the details given the information given. So I know enthalpy of formation of calcium chloride is enthalpy of atomization of calcium is plus 193. First ionization energy of calcium is plus 590. Second ionization energy of calcium plus 1150. And then that's the enthalpy of atomization of chlorine. So plus 121 times by 2, because I've got 2 moles of chlorine. And then that is the electron affinity of chlorine minus 364 from here to here, but I need to times it by 2 again. So the enthalpy of lattice dissociation of calcium chloride. Lattice dissociation. Well, what I'm going to say is I know enthalpy of formation of calcium chloride is minus 795. So I'm going to say minus 795 plus y equals 193 plus 590 plus 1150 plus 121 times by 2 plus minus 364 times by 2. And I think that's the tricky part, identifying that's 2, so you need to double it for the ones for calcium, for chlorine, sorry. So for this you need to double it, for this you need to double it, your value, and also what enthalpy of lattice dissociation is, and then you get y equals plus 2242 plus 22 plus 2242 because it's multiplied by 1 Given the equation includes state symbols to represent the process that occurs when the entropy of solution is measured. Entropy of solution. So I'm going to go for magnesium chloride, which is a solid, to its ions, because it's in solution now. Mg2 plus aqueous plus 2Cl minus aqueous. Part E, use your answer to part D and data in table 2. So your answer to part D, which is this, and the data in table 2, okay, this, to calculate a value for the entropy of solution of magnesium chloride. Okay, so my equation here is here. I'm going to write it again here because I'm going to have to do something else to this equation. MgCl2 solid, I'm going to Mg2 plus aqueous plus 2Cl minus aqueous, and I'm going to write on the bottom Mg Mg2 plus solid plus 2Cl minus solid, and I'm going to calculate value for the entropy of solution of magnesium chloride. Well, that's entropy of solution. I know the entropy of lattice dissociation is that. I know the entropy of hydration is that. So what I'm going to say is I'm going to say Y plus 2493, Y plus 2493, no, sorry, Y equals 2493 plus 2493 plus minus 1920 plus minus 364, but that needs to be multiplied by 2 because I've got 2 moles of Cl minus. So Y equals 2493 plus minus 1920, or minus 1920, plus minus 364 times by 2, and you get minus 155. And let me just double check that in my calculator. I'll just put brackets around it. Yeah, minus 155 kilojoules multiplied minus 1. The entropy of hydration of Ca2 plus gases is minus 1650 kilojoules multiplied minus 1. Suggests why this value is less exothermic than that of Mg2 plus gases. Mg2 plus gases, the entropy of hydration is minus 1920, and this case is minus 1650. Now, anytime you get a question like this, well, let's have a look. It's calcium and magnesium, right? Calcium, magnesium. I already can tell the Ca2 plus ion is going to be bigger, definitely, and that's all it wants you to really say. So the first mark you'd get is by saying Ca2 plus has a bigger charge to size ratio, weaker attraction to oxygen delta negative in water. Ca2 plus has a bigger charge, to size ratio than Mg2 plus. Weaker attraction. Explain why the standard entropy value for carbon dioxide, which is, I'm looking at this table then, for carbon dioxide, is greater than that for carbon. So 214 and 216. Well, one thing I can spot is that carbon is a solid, and that's obviously a gas. And entropy measure the number of ways that particles can be arranged and the number of ways energy can be shared out between those particles. Well, if it's a gas, I just need to state carbon dioxide gas is more disordered. More disordered. And that's the key term, disordered. State the temperature at which the standard entropy of aluminium is 0. The temperature at which the standard entropy of aluminium is 0 is going to be 0 Kelvin. And then it says use the equation data in the table to calculate the minimum temperature where this reaction becomes feasible. And this is 7 marks, this part, okay. So the minimum temperature at which this reaction becomes feasible. Okay, well, let's write down our equation that we need to use. Delta G equals delta H minus T delta S. And I know I need to work out delta S, and then I need to work out delta H. So that's why it's 7 marks, okay. But it shouldn't be anything too complicated. Delta S equals delta S of products, which is 4 times by 6. You know what, I'm just going to put this on my calculator. I'll walk you guys through it. So delta S is going to be delta S of products, 4 times by 6 plus 3 times by 214. So 666 minus delta the entropy of reactants, 2 times by 51 plus 4 times by 28 plus 3 times by 214. Yeah, I did that wrong. That should be 754. 754 minus entropy of reactants, 2 times by 51 plus 3 times by 6. Yep, 120. 754 minus 120 is 634. And obviously remember, delta S is measured in joules k to the power minus 1 multiplied by minus 1. There's 100% going to be a changing between units thing going on here. Of course there is. It's 7 marks. Okay, and then I need to work out delta H. Well, delta H is, well, it tells me, how do I know? Because if I zoom in, zoomed in a bit too much, but yeah, if I scroll a bit up and then move here, can I do that? There you go. Here, this little F symbol tells me that it is formation data. So because it's formation data, I'm going to use the formation formula, enthalpy of products minus enthalpy of reactants. But if it was combustion data, I would use the other way around, the formula the other way around. It's very important you see that, because don't assume the data. Don't assume the data. Actually read it and then have a look at it. So all it's going to be is 3 times by minus 394 minus 2 times by minus 1669 2156. So delta H equals 2156. And what is it measured in the units? Kilojoules mole to power minus 1. Kilojoules mole to power minus 1. Now I want to find out at which this reaction becomes feasible. Well, when this reaction becomes feasible, delta G equals 0. The minimum temperature at which the reaction becomes feasible, delta G equals 0. Therefore, I get T delta S equals delta H, and therefore T equals delta H over delta S. And I want my units in Kelvin, so I need to now think about converting between units. I'm going to convert my delta S into kilojoules multiplied by -1. So it's going to be 2156 divided by 0.634. So 2156 divided by 0.634, I get 3400 Kelvin. 3400 Kelvin. Very nice, 7 marks. This comes up in the exam, you should be pretty happy. Because it's just memorizing a formula, identifying minimum temperature at which reaction becomes feasible, delta G 0, and then you find delta H using a table, you find delta S using the table, convert your units, substitute into this formula. That's it. Question 3 is question about enthalpy change. The figure below shows a Born-Haber cycle formation of strontium chloride. It doesn't want me to fill in the gaps, which it usually does. It just wants me to calculate value for electron affinity of chlorine. Okay, so electron affinity of chlorine is what? Well, it's going to be this part, which I'm going to label as X. Okay, so I'm going to say, what am I going to say? Well, what is the enthalpy of lattice formation? -2112. Enthalpy of formation, I'm going to let enthalpy of formation equal to everything else. So I'm going to say -828 equals 164 enthalpy of atomization of strontium. 164 plus the enthalpy of atomization of chlorine, 121 times by 2, plus first ionization energy strontium 548, plus the second ionization energy of strontium, which is 1060, plus 2. The reason it's 2 is because it's chlorine, right? And this is the enthalpy electron affinity of chlorine. So 2y minus 2112, rearrange the equation, you get -365. Again, there's only three parts they could ask you about with this. If they give you this, fill in the gaps, which is most students don't struggle with that. They might struggle with electron affinity, including myself, so then you need to review that. Or this kind of question where you just need to know what is the electron affinity, what's this bit, and then how do we do it, a method, learn it beforehand, and then that's it. Draw a line from each substance to the enthalpy of lattice formation of that substance. Magnesium chloride, magnesium oxide, barium chloride. Yeah, I'm gonna do this for a different video because I don't even understand this question as well myself. So I'm gonna ask my teacher. Sorry guys. Okay, state what is the difference between theoretical and experimental values. Has covalent character. You know, has covalent character. Explain by entropy of hydration becomes less exothermic from lithium to K. Well, just look at the periodic table. Lithium to K. K is further down the group. You're going further down the group. So what's going to happen? Well, you could have more electron shells, larger distance between nucleus outer electrons, large ionic radius, electrostatic attraction between what and what decreases. So size of ion increases, and that's not a good thing, you know, because size and ion increases, electrons are further away, etc. Ionic radius increases, etc., etc. But I'm going to say size of ion increases, and therefore the I'm going to type this up. Electrostatic attraction between metal ion and oxygen delta negative of what is hydration, so it's of water decreases. Use Davidson table 4 to calculate entropy of hydration of bromide ions. Again, you have to be confident with constructing these cycles. Calcium bromide. Well, let's break it up. Calcium, say 2 plus, bromine, Br minus, so it's going to be CaBr2. You have to be confident because they're going to ask you about this. What is it? Entropy of hydration. Well, that's going to be Ca plus aqueous plus 2 Br minus aqueous. And if you start from the bottom here, well, I'm going to have Ca gaseous plus 2 Br gaseous. Or plus Br2 gaseous. I don't think it really matters. So I want to find the entropy of hydration of bromide ions. So, okay. I know the entropy of solution is minus 110. Remember, this is the entropy of solution. Entropy of solution. How do I know? Because I'm getting the aqueous ions because I've dissolved it in the solution. Entropy of lattice formation of calcium bromide is minus 2176. But what does that mean? That means if I'm going this way, it's minus 2176. But I'm not. I'm dissociating it. So it's going to be plus 2176. And the hydration of calcium ions is minus 1650. So now I'm going to have to construct the equation. So I'm going to say minus 110 equals 2176 plus minus 1650 plus 2y. 2y equals, no, forget that, y equals, so minus 318. Minus 318. So let's check the mark scheme. Minus 110 equals 2176 plus minus 1650 plus 2y minus 318. They allow you to use the formula. Just they're never gonna ask you just to use the formula for this case. I don't think they will. So this method is just foolproof. It's like bulletproof. Like you ain't gonna fall for the trap. But we have to memorize the formula, and then that. Just learn how to do this. Question 4: Methanols form a carbon dioxide and hydrogen react, and it wants me to calculate Gibbs free energy change. That's it. And then there's a second part, but we'll have a look at that later. So Gibbs free energy change, delta G equals delta H minus T delta S. Can you guys still? Yeah. So I'm gonna have to find out delta H. Well, again, zoom in, check what it says. Well, I can see there's a little F there, very tiny F. So that tells me it's formation data. So then therefore what formula I'm going to be using, I'm going to use enthalpy of reactants, enthalpy of products, sorry, minus enthalpy of reactants, formation data. So products minus reactants, I'm just going to put it in my calculator. It's going to be minus 21201 plus minus 242 minus 443 minus 443. But obviously in the exam, show every step you're working. It's 6 marks. So obviously, if you don't show you're working, I don't think you're going to get that many marks. Minus CO2 minus 394. That's it, because hydrogen 0. Minus 394. Delta H equals minus 443 minus 394 minus 49. Minus 49. And what is that in? That's in kilojoules moles to power minus 1. Mole to power minus 1. That's going to become very important later on, and I'll show you guys why. I think a lot of you guys probably already know. Then entropy of products minus entropy of reactants. So 238 plus 189, 427 minus 214 plus 3 times by 131, 607. Delta S equals 427 minus 607 minus 180, and that's obviously in joules k to power minus 1 mole to power minus 1. And I want delta G. Well, delta G is delta H minus 49 minus T, temperatures in Kelvin, 890, delta S. Well, delta S is 180 minus 180 joules. I want delta G in kilojoules, so I need to divide it by 1000. So it's minus 0.180, and that's really important because that's where most students go wrong. And then that's why they ain't going to get the final mark or the final 2 marks. And you should get 1, 1, 1, 1, 1, 1. So let's have a look at the mark scheme. The mark scheme says find out delta H minus 49, find delta S minus 180. Recall this equation. Yes, always write down the equation. If you mix up the equation, then you're not going to get anything else right. So write down the equation first time. And then minus 49 minus 890 times by 0 minus 0.1 minus 0.180. Perfect. Okay. The second part, the graph below shows how the Gibbs energy change varies with temperature in a different gas phase reaction. Straight line graph of this gas phase reaction being extrapolated to 0 Kelvin. Okay. Use values of intercept and the gradient from the graph to calculate enthalpy change. Well, let me just write down the equation again, and hopefully you guys can see something. Delta G is delta H minus T delta S. And from GCSE maths, even if you don't do A-level maths, straight line. This is quite clearly a straight line. So I'm thinking y equals mx plus c. Okay, so if I put them next to each other, mx plus c, that tells me y is that, c is that. The gradient is entropy change. X is the temperature. Okay, now it makes a lot more sense. It does tell me the question. Actually, no, it doesn't. So I know delta H is C, which is what is C also known as? The y-intercept. Intercept. So if I go here, y-intercept is when x equals 0, and I zoom in, and I go here, sorry, here, and I go a bit up, and I can see when it intersects. There we go. It is, well, that's 125, 130, 135, 140, 145. So that is delta H. So just from that, I've got delta H, 145. 145. I'm going to put a plus because why not? Plus 145. Now the gradient. The gradient tells me delta S. I've decided that. But it's negative delta S. So I'm going to write that down. The gradient equals negative delta S. So let's work out the gradient. Now I'm not going to do this, but it's pretty simple. y2 minus y1 over x2 minus x1. And you should get the gradient as 0.167. Well, you get minus 0.167 equals minus delta S. Negatives cancel out. You get delta S equals 0.167. Okay, so that's it. Let's move on. And if you do that, you're not going to get it correct. Delta S equals 0.167. But if I read the question again, it wants my entropy change in joules k to the power minus 1 mole to the power minus 1. Look at that. What would this give me? This would give it me in kilojoules, because look at that. That's in Kelvin, which is the correct unit. That's in kilojoules. So that will give me delta S. So I'm going to write that down here. That will give me delta S in kilojoules mole to the power minus 1. So therefore I need to then times by 1,000. So therefore my answer is going to be 167. Positive 167. Now you might say, man, yes, I'm obviously going to spot that you need to time by 1,000 for that because of that. But in the exam conditions and the time pressure, it's very easy to make that mistake. It's very easy to make that mistake. And so I just want to point that out by making that mistake. Part C, state what the graph shows by the feasibility reaction. So a lot on this graph, but I can see, well, feasibility is when delta G is 0 or negative. So that's when it's feasible. That's when it's not feasible. So above the temperature 800 and something, the reaction is feasible. Below the temperature, that the reaction is not feasible. That's what you have to say. So above 845 Kelvin, the reaction becomes feasible, and below 845 Kelvin, the reaction is not feasible, or thermodynamically feasible, whatever you want to say. But yeah, please guys, anytime you see this, they're probably all going to use this in my year for 2025. Straight line graph, y equals mx plus c, compare it, and then carry on from there. Okay, complete diagram. So I'm going to have cs plus gaseous plus E minus plus I gaseous. I'm also going to have CS solid plus a half I2 solid. Yes. So CS solid plus a half I2 solid, C plus gaseous plus E minus plus I gaseous. That's it. Nice 2 marks. Use diagram to calculate standard entropy of atomization ID. So what I'm going to say is I'm going to say entropy of formation minus 337 minus 337 equals everything else. So minus 337 equals, well, the entropy of atomization of cesium, which is 79, plus the entropy of atomization of iodine, which is a Y, plus first ionization energy 376 minus 314 minus 585, and I get Y equals 107. The entropy of lattice formation of cesium iodide is a value obtained by experiment. Value obtained calculation is minus 582. Cesium iodide, entropy of lattice formation of cesium iodide minus 585 minus 582. Well, they're very, very similar, so I'm just going to talk about. Now, there's two things you could say. You could say purely ionic, or you could just say very little to non-covalent character. And I'm going to use that one because purely ionic, yeah, but covalent character is a thing you can always use for these kind of questions. So let's just stick with that kind of theme. Use data from table 2 shows the reaction is not feasible at 298 Kelvin. So data to table 2, well, that's table 1, this is table 2. Okay, well, write down your equation. Delta G equals delta H minus T delta S. Delta H is up. Delta S I'm going to have to work out, unfortunately. Actually, no, it's pretty fine. Now, first things first, this is formation data, right? Delta S entropy of products minus entropy of reactants, 82.8, it should be, plus a half times by 117 minus 130. That'll give you 11.3, and that's in joules K to power minus 1, mole to power minus 1. Then write down the equation, and then delta G equals delta H 337 minus temperature 298, and then delta S, which is that, right? No, I run it in kilojoules, so 0.0113. 123, yeah, 0.0113, and then you get delta G as plus 334. So I'm going to write down delta G equals plus 334, and then you can just say your normal stuff, because delta G is positive, therefore reaction not thermodynamically feasible. In order for reaction to be thermodynamically feasible, delta G needs to be negative / less than 0. Just say that, but it's not necessary. Part A, complete diagram. Okay, well, I'm gonna have, so I've got entropy, first ionization, Mg magnesium, that's gonna be that, then Mg plus gaseous plus E minus plus O gaseous, then the second ionization energy, Mg2 plus gaseous plus 2E minus plus O gaseous, then the first electron affinity, which is just going to be, so Mg2 plus gaseous plus 2 minus plus O gaseous, Mg plus gaseous plus E minus plus O gaseous. First electron affinity for oxygen. Okay, so it's going to be O minus gaseous plus Mg2 plus gaseous stays the exact same thing. But I'm adding electron because I need the charges to overall balance out to 0. Okay, and then yeah, that's the second electron affinity. Well, that second electron affinity of oxygen, so that becomes O2 minus. Therefore, we don't need electron anymore. That stays exactly the same. So remember, when it says first ionization for magnesium, that's the only thing that's changing. You're not affecting oxygen or anything. First electron affinity for oxygen, that is the only thing that's going to change, not magnesium. And that was for 3 marks. Okay, and then it says calculate value for entropy of lattice formation for magnesium oxide. So it's just the same old. I'm gonna say the enthalpy of formation minus 602 equals everything else equals enthalpy of atomization of oxygen, which is no wait, yeah, no, bond dissociation energy for oxygen, a half. Wait, what? A half times by 496 plus the thingy for magnesium 1150 plus first ionization energy 736 plus second ionization energy 1450, and then electron affinity, first electron affinity minus 142, then second electron affinity plus 844, and then plus a y, and then you get y is minus 3888. I'm going to minus 3888. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? Now, let's say I don't know anything about this definition or anything, or how to construct the equation. I can already cross two out immediately. And those two are B and D. 2 moles. I'm forming 2 moles. When has it ever been 2 moles? It's never ever been 2 moles. It's always 1 mole. Okay, now I'm left with A and C. Well, A, it says going from gaseous to gaseous. Iodine is gaseous. And then A is saying from iodine solid. Well, therefore, yeah, it is going to be A. So just by using logic, you can solve that. Obviously, you do need to know some knowledge, but yeah. Lattice entropy values can be obtained from Born-Haber cycles by calculations based on a purely perfect ionic model, which comprises the greatest percentage difference between these two values. Cesium or lithium. Now, if I look at cesium and lithium, lithium is here, cesium is way down the group in group 1. So I know cesium is going to have, it's going to be very, very big cesium. Okay, well, I know cesium is comparatively bigger compared to lithium. But if I look at iodine, right, that's a really big negative ion. And if I look at lithium, it's a very small positive ion. So that's how you would think about it. Okay, break them down into the ions. Cesium is big, it's big. Whereas lithium, the Li plus ion, is very small charge and all of that. So the polarization. And then I've got fluorine and or iodine. Well, the thing about fluorine is it's also very similar to lithium. They're both very small, but with iodine, it's comparatively bigger, the ion minus ion. So therefore, it's going to be D. That's going to show the greatest percentage difference between these two values. Once you do it like that, that makes so much more sense because if it's going to show the greatest percentage difference, it's going to have a very small cation and a very big anion. Define the term entropy of lattice formation. The entropy change, 1 mole of solid ionic compound is formed from its gaseous ions. So entropy change when 1 mole of a solid ionic compound is formed from its gaseous entropy change. 1 mole of a solid ionic compound is formed from its gaseous ions. Use the data table to calculate entropy of lattice formation of silver iodide. First things first, you have to draw out what's going on. So AgI solid to Ag plus aqueous plus I minus aqueous. Hopefully you get the point. Just haven't got enough space here. Ag plus gaseous plus I minus gaseous at the bottom. Arrows going downwards, arrows going upwards. I want to find the entropy of lattice formation of silver iodide. I know to go from here to here, it's plus 112. And I know to form these aqueous ions, it's minus 464. I want to find out the entropy of lattice formation of silver iodide. So I want to find out this. That's what I want to find out. So I'm going to say 112 equals, well, let me go down. Wait. Entropy of lattice formation. Oh, yeah, I could just go the other way around. If I want to find out this, I can just say I go this way. Going here is the same as this way and this way. So I can say y equals 112 plus 464 plus 293. So I get plus 869. But that would give me to wait. Okay, let me go through it again. So I'm going that way and then down. I want to find the entropy of lattice formation of silver iodide. And I want to find the entropy of lattice formation of silver iodide. Okay, yeah. My way is perfectly fine. 112 equals y minus 464 minus 293. Wait, minus 464 minus 293. Sorry, minus y. Because think about it, guys. That's y. But I don't want that. I want this. Right? So I'm going to say 112 equals minus y minus 464 minus 293. And then you get minus 869. Bit of a weird one, that one. Calculation entropy of lattice formation silver iodide is gives smaller numerical value than the value calculated in part B. Explain this difference. So again, always talk about covalent character. So silver iodide contains some covalent character, hence forces holding the lattice together are stronger. If I identify a reagent that could be used to indicate the presence of iodide ions, silver nitrate, yellow precipitate. Okay, not that many questions left. Yeah, very few questions left. I was contemplating about whether to make this video or not because I saw what 22 pages and I was like, oh, that's gonna take ages. Hasn't taken too long. Okay, calculate the Gibbs free energy change and then using analytic explain directions. Feasible delta G equals delta H minus T delta S. Delta G equals minus 60 minus add 273, need it in Kelvin. 1262 bracket delta S. Well, delta S is products, entropy of products minus entropy of reactants. So it's going to be 2 times by 198 plus 253, 649. So delta S, obviously you're going to have to show the working out as well. 649 minus 50.2 plus 2 times by 5.70 plus 2 times by 223, 507.6, 7.6, 649 minus 507.6. But remember, that's in joules k to power minus 1, mol to power minus 1. I want my answer kilojoules, so now I get 141.4 joules k to power minus 1 and mol to power minus 1. But now I need to put it in here, so I need to convert it to kilojoules. So it's just going to be that times by 10 to the power minus 3, which I can already do in the top of the head. 1, 2, 3, 0.1414. So it's going to be minus 60 minus 1262 bracket 0.1414 minus 238. And then experimental reaction is feasible. Well then, hence reaction is, I like saying this, thermodynamically feasible. Makes me think I'm smart. Thermodynamically feasible. And I'm not going to say delta G, I'm just going to say delta G inequality less than 0. I'm going to say it's negative or like that. There you go. And that was, how many marks was that? That was 6 marks. The explanation should go there though. So my apologies. Suggest one reason why enthalpy change cannot be determined directly by calorimetry. Not possible to prevent some dissolving. Calculate enthalpy change for absorption of water by mgCO2 to form that. Wait, what? Calculate enthalpy change for the absorption of water by mgCO2. Well, delta H is, let me just read this question again. Obviously it's 2 marks, it can't be difficult. Delta H is going to be, okay, calculate enthalpy change. So delta H equals minus 39 plus, no, sorry, minus 39 minus 155. No, it's not. Minus 39 minus 155. It's not that, is it? Okay, let me just stick with my word. Like I always said, draw the cycle out, but this one's just very weird. So MgCl2 solid plus 4H12 liquid to that thing. I'm just going to let that equal y for now because I don't want to write all of that thing. And then if I go down, that's minus 155. And then I want to get back up, but that's not going to be minus 39, that's going to be plus 39. So it's going to be minus 155 plus 39, which is minus 116. So yeah, just use the same principle like that. Part C, describe how you would carry experiment to determine the entropy of solution of this. Explain how results use count the entropy of solution. This is actually a very nice question. This is so stage one your method. Measure water with beaker. Use a suitable mass in range 10 to 100 grams into polystyrene cup. Add known mass of magnesium chloride solid. And then the use of before and after weighing method. Stage 2, your measurements. Record initial temperature. Record time at regular temperature, regular time intervals until a trend is seen. And plot T versus time. Stage 3, extrapolate lines to when solid added. And then find delta T. I probably should draw that, shouldn't I? Find delta T from graph at point of addition. At point of addition. Okay, and then moving on. Use data to plot a graph. Okay, plotting the graph bit is going to be very annoying. And then calculate gradient. Okay, so this is what I mean. You can get this kind of question where plotting the graph 5 marks. It wants you to plot the graph, which it gives you everything, right? But I'm just gonna copy from the mark scheme because that's not really what the main thing is. The main thing is calculating the gradient and then hence calculating the entropy change. And there's a very, very, very small trick that I think I would fall for, and a lot of students would fall for. Oh yeah, for this one, then once you find out the thingy, the delta T from point of addition, then Q equals MC delta T, and then find out the moles, and then yeah, you can find out the entropy of solution. So I plot the graph. And I'm just going to quickly copy from the mark scheme because that's not what I want to go through right now. Okay, get the graph. There's only 1, 2, 3, 4, 5, and then you get a straight line. That's the main thing. You have to get a straight line for the rules to apply. So yeah, mind the straight line. But yeah, because once you've got a straight line, now you can compare them. Well, y equals mx plus c. Therefore, must be a straight line. Must be a straight line. If you're getting a curve or something, then you've clearly not plot them correctly. And then obviously I'm comparing it to delta G equals delta H minus T delta S, and I know delta H is C, I know T is X, and I know minus delta S is M. So I know gradient equals minus delta S. Okay, so the gradient is, I get 0.167 equals minus delta S. Delta S equals minus 0.167. But if I'm using this with kilojoules multiplied minus 1, this is in Kelvin, I'm therefore going to get delta S in kilojoules multiplied minus 1. But that's not what I want. I want delta S in joules k to the power minus 1. So therefore I have to do the gradient times by 1000 minus 167 joules k to the power minus 1 multiplied minus 1. If I scroll up a couple more, same thing applied for one of these questions again here. I think I would pass. Yeah, it was this one. But in this case, you would get delta S, and then yeah, you need to times it by 1000 for part B. Sorry, you get delta S is 0.167. No, you need times by 1000, 167. And again here, I got 167 as well, but this case got negative. But they always love to test you on that. How well do you know your units? How well? Not only do you know your units, anyone can tell me the units, but how well are you going to be able to spot it in the exam and then convert them? Question 12, a reaction is exothermic. So exothermic meaning delta H equals a negative 7, let's say for example, just a negative number, and there's a negative entropy change. Entropy change equals negative 14. What is correct about the feasibility of reaction? So delta G equals delta H minus T delta S. I've got delta H is negative, and I've got delta S is negative. Well, if both delta H and delta S are negative, that tells me the reaction is feasible at lower temperatures, so below a certain temperature. So the reaction is feasible below a certain temperature. Yeah, that's what it tells me. Reaction is feasible below a certain temperature. And that is the end of this question paper.